Hey guys, it's Mr. Post, and on today's video we'll be learning how to determine the limiting and excess reactants in stoichiometry problems. A good analogy we're going to start off with is, it's time for a barbecue and we want to make hot dogs on the grill. Okay, and limiting and excess reactants actually do come into play here, because what we're going to find out is that when we make the final goal here of making our hot dogs, all right, we want to make a hot dog. We're having a party, right? All right, we get a pack of hot dogs, get some buns. The number of hot dogs I make here, right? What is the maximum amount of number I can make? And it actually all depends upon what my ingredients are and how much I have of them. So if we look at this here, okay, I have a standard hot dog pack here, hot dog buns. We got probably 8 rolls inside there. Okay, let's check this out. I got 1, 2, 3, 4, 5 hot dogs. So the gist of this is the maximum number of hot dogs I can make is going to be 5. Okay, what's going to happen is that once the hot dogs run out, the number of hot dogs I can make is going to be stopped. I can't make any more hot dogs once I run out of my dogs over here. Okay, I'm going to have a little bit of extra going on. The extra I have is going to be the buns. I had 8, I only used 5, so now I have 3 left. And the gist of this is whatever reactant or ingredient runs out is going to be called the limiting reactant. Alright, so hot dogs is known as, in this case, my limiting reactant. What's it going to be limiting? Why do we call it limiting? Because it only limits us to making 5 hot dogs. Now the buns, with the buns we had the potential of making 8. We had the potential of making 8. We have 3 left over. Alright, so this is going to have a name as well. It's going to be called the excess reactant. Okay, so once again, it's a good analogy actually for exactly what we're going to do today. And our reactions today, we're going to be seeing something like instead of hot dogs, we're looking at magnesium, and maybe instead of oxygen, instead of hot dog buns, we're looking at oxygen, and we're going to make something that's going to be magnesium oxide. And the maximum amount we can make really depends upon which one of these 2 reactants or ingredients runs out first. The second one of my ingredient runs out, I am limited to the number of product I can make. All right, so let's get to some actual text here. The text we're going to read here is that my limiting reactant is the reactant, the starting product that is used up in a reaction. And once it is used up, big thing here, the reaction stops. Once the reaction stops, I'm going to have some reactant left over. The reactant that was not used up is called the excess reactant. It is the one that is left over. Certain reactions can be designed perfectly where you don't have any excess reactant and both of them are used up. That's perfect, but unless you actually do a very, very perfect reaction, you're not going to find that. Often, whether you're making something on the grill here, breakfast, you name it, you often find like, oh my gosh, I have to run to the store because I don't have this, and that is going to limit what I can make. All right, that's the main point here. We're trying to find out what's the maximum I can make of something, in this case a chemical, and we're going to look at which one of my reactants is the one responsible for eliminating it, in this case, the 5 hot dogs. So let's start out with a problem here, okay? This is a problem that's not balanced right now. We're going to balance it in a second, but it's magnesium reacting with oxygen to produce magnesium oxide. Okay, and in order to do this problem successfully, we do need to balance it, and it's to be balanced with this. All right, so those are the coefficients we're going to use to balance. If we react 15 grams of Mg, all right, so I'm just going to stop right now. I have 15.5 grams of Mg. And I'm going to react that with 20 liters of O2. And let's just make it, for our purposes, 20 with a decimal point. Okay, so I have 20 liters of O2. Which one of my reactants is the limiting reactant? And also, how much product can be made? Okay, so I'm looking for product. We're going to identify magnesium oxide in grams because it ends up being a white powder, so we'll measure it in grams. So I'm starting off with 15.5 grams of magnesium. I'm also starting out with 20 liters of oxygen, and I want to find out which one of these will limit the amount I make of this. And when I do, how much do I make? And so really what you have here, guys, is 2 problems. You have 2 problems with 2 different givens. One problem is going to have a given that is 15.5 grams of Mg. So let's begin that. And the second problem is going to have the given of 20 liters of oxygen. Okay, the both are actually going to go to the same ending. We're going to have the ending in this case be grams of magnesium oxide. And this one goes to grams of MgO as well. So the whole point here we're trying to find out is how much magnesium oxide can be produced. What's the maximum amount? And if we use dimensional analysis, we're going to go through this problem and we're going to find out how much MgO can be produced maximum. Okay? Now the deal is this. Whichever of these runs out first will limit the amount I make over here. Okay, so you're going to see how this works in 2 seconds. We're going to now convert from magnesium to magnesium oxide using some dimensional analysis. Let's break it down. Okay, go ahead if you want to solve the problem right off the bat. You can press pause on this one. Go ahead, solve it. You should be able to. Okay, I'm just going to work through the problem, and then I'm going to come back on it. Okay. Okay, guys, we're back, and I've worked the whole problem out. Basically, I've taken magnesium as one of the active ingredients here, and I've converted it into magnesium oxide. And I went through all of dimensional analysis, canceling out my units along the way, mole ratio, and finally converting it using the molar mass of MgO to find out that if I use up all of my 15.5 grams of magnesium, I should produce 25.7 grams of magnesium oxide. Okay, so that's one of the ending results here. Now, if I used up all of the other ingredient, my 20 liters of oxygen, and I go through and cancel out my units along the way, okay, everyone cancels. Here I am, 40.3 once again, and I end up with 72 grams of magnesium oxide. Now, you'll notice that these two numbers are different. Okay, once again, in order to use up all of my oxygen, I should make 72 grams of magnesium oxide. In order to use up all my magnesium, I should make 25 grams of magnesium oxide. So what you're going to see is that the second I use up all of my magnesium, I have made only 25.7 grams of magnesium oxide. So really, the most magnesium oxide I can make is 25.7 grams because that's when this runs out. I run out of magnesium. Oxygen I have left over, and I know I have it left over because it has the potential of making 72 grams of magnesium oxide. So in this reaction, magnesium becomes my limiting reactant, and oxygen becomes my excess reactant. Excuse me there. And how much magnesium oxide can I theoretically make? The most I can really make is 25.7 grams. Okay, guys, on our very last example for the day, we'll check out this one here. We got calcium reacting with oxygen to produce calcium oxide. Let's balance this thing out. It ends up being a 2-1-2 affair here. And let's just say I begin with, let's make up a number, 35.1 grams of calcium. And let's make up another number. Let's say I'm reacting with, let's just say 37.1 grams of O2. Okay, and the question is, how many grams of calcium oxide will I make? And also, what is my limiting and excess reactants? Okay, the reaction is balanced, so we can begin. I have two givens here. I have 35.1 grams of calcium, and I also have 37.1 grams of oxygen. Both these are going to be taken to the same thing. The thing I want to find out is how much CaO will I make? And so both of these will have the same ending. One of the things I always do to start all my problems is write down the givens. The givens on this side and the givens on this side. And that means the very last box here should be grams of CaO, and the very last box is grams of CaO. And that's going to be the molar mass, the mass of 1 mole. And the mass of 1 mole of this should be around 56 grams. That's per 1 mole of CaO. Okay, just a nice little habit I like to get into here. That should be CaO. And now I begin the problem. Okay, let's begin the problem here. We have 1 mole of Ca, which is going to weigh around 40 grams of Ca. And likewise, 1 mole of O2 is going to have a mass of 32 grams of O2. All right. In the middle here, we have what's known as the mole ratio step. The mole ratio step is going to convert from the first unit of oxygens into calcium oxide at the other side, and likewise from calcium to calcium oxide over here. So we need a ratio that actually bridges calcium and calcium oxide. And up here I see I have 2 moles of Ca per every, in this case, 2 moles of CaO. And on the bottom, I'm going to have oxygen on the bottom, and oxygen is 1 mole. and CaO we saw before was 2 moles. Okay, let's calculate it out, guys. Okay, guys, when the numbers are crunched, what I end up with is that if I want to use up all of my calcium, 35.1 grams, the most calcium oxide I can make is 49 grams. And likewise, if I want to use up all of my O2, my 37.1 grams of it, the most calcium oxide I can make is 130. So really, if you look at the two numbers, the most calcium oxide the reaction can make is limited. It is limited to 49.1 grams, because once all my calcium is used up, I will have made 49.1 grams. And once calcium is used up, the reaction stops. So the reaction stops after 49.1 grams of calcium oxide is made. So calcium becomes my limiting reactant, limiting the amount of calcium oxide I can make. Likewise, oxygen is going to be left over, so we're going to call it the ER, also known as the excess reactant, because it has the potential of making 130 grams of calcium oxide. Alright guys, that's a simple, straightforward way of how we calculate limiting and excess reactant, and not just that, how much of the product I can make with that limiting reactant. Okay guys, thanks a lot for tuning in. Have a good day. Later.